People don't usually notice things until they're inoperable or we don't have them anymore. Such is the case with water. When customers ask about their tap water, they just want to know if it's safe to drink. They're often unconcerned and uninformed as to how water gets to their tap from the original source. It's not until there's a water quality issue or disruption in service that triggers questions from consumers about their water service. Water follows a complex path from its source, passing through the treatment plant and into a collection of pipes and structures, eventually finding its way to a customer's tap. While safe and ready to drink when it leaves the treatment plant, as water passes through miles and miles of distribution system piping, reactions that degrade water quality can occur. Factors affecting water quality may include nitrification, iron and magnesium buildup, other leached or settled materials, organics or high water age in slow flow or dead-ended systems. To prevent or correct these types of problems, it's important that every utility has a water main flushing and cleaning program. Water mains are the arteries of water delivery. Within the largest system pipes, flow tends to be slow, except in times of firefighting. Because of this, corrosion products, scale, and other solids settle to the bottom of the pipe. The development of corrosion products on the inside of pipe, called tuberculation, and other collected materials eventually further reduces flow and can cause taste and odor problems. Sediment inside the pipe may also harbor bacteria and biofilm growth that can consume any residual disinfectant. Without disinfectant in the distribution system, bacterial growth may increase dramatically and threaten public health. In short, when the system isn't flushed, biofilm buildup increases, water quality decreases, and customer concerns and complaints increase. Regular flushing and cleaning improves water quality, system performance, and reduces public health risks. The most important aspect of any flushing program is planning. A plan should be mapped using computer-generated distribution system maps, supplemented with geographical information systems or GIS data. Mapping helps decide a flushing order and pattern and determines the location and position of valves and hydrants in the system. When a system is flushed, work should start closest to the treatment facility, water storage facility, or pump station and expand outward. If only certain areas are to be flushed, the process should still start at the point closest to the potable source. The amount of water needed when flushing can be estimated by calculating the volume in the pipeline and the flow from the hydrant. Operators will learn through experience how often or how long certain areas should be flushed. Before flushing, crews should verify that all valves and hydrants are operational. Hydrants that will be used for flushing must be opened fully. System pressure and flushing rates or velocities can also be simulated, mapped, and modeled. Utilizing the computer model is the most efficient system for flushing. When flushing, local fire and police departments should be notified. In many areas, firefighters will assist in a flushing program since it offers an opportunity to train and check the proper operation of fire hydrants. Public notification is also very important. The media should be contacted and provided with projected flushing dates and locations. The utility should post the information and progress on its website, distribute the information door-to-door in targeted areas, and/or customers should be notified by phone, mail, or email. Customers need to be advised to flush their service lines following main flushing. Usually running the equivalent of a bathtub of cold water will suffice, or until water runs clear. Following flushing, customers should be told that the water is safe to drink, but care should be used in making sure the water runs clear before washing clothes to prevent staining. The physical grounds adjacent to the flushing areas should be checked for potential drainage problems. The inspection should ensure that discharged water will not flow into basements or excavations. Storm drains should also be checked for blockage. Flushing programs can be proactive, as in routine or system-wide, or reactive, as in emergency or in response to a color or taste and/or odor event. Flushing procedures vary with every water provider. but three methodologies are generally accepted: an isolation method, directional flushing, and a continuous blow-off method. The isolation method is typically used following a color, taste, and/or odor event reported by a customer. Materials stirred up in the main or stagnant water due to low flow may be the cause of the water quality problem. Flushing the area will usually mitigate the problem. The isolation method pinpoints or isolates a particular area of a distribution system. Valves and hydrants are marked and a flushing pattern is created. Then, following a set schedule of opening valves and hydrants, the area is flushed until water from the hydrants runs clear. The crew then proceeds to the next area that needs flushing. Directional flushing follows the path of the distribution system, moving from the treatment plant outward, from larger pipes to smaller. Crews create a path of cleaned pipes with the unflushed areas remaining ahead of them. When utilities use reactive flushing in response to customer complaints, the process usually only improves localized water quality temporarily. Directional flushing provides a long-term solution because it uses a higher velocity and flushes from a potable source outward. It is a whole systematic approach rather than a responsive one. To perform directional flushing, isolate the main, close the valve off, bring water from the clean source and flush the main, take a chlorine and turbidity reading out of the fire hydrant. When the turbidity reading reaches about 1 NTU and the chlorine residuals are up, the water inside the main is clean. Higher than normal turbidity levels may require low volume or low flow flushing, less than 3 feet per second, to avoid scouring the water main, which may cause more water quality issues. Directional flushing is very successful in removing biofilm, and by concentrating flow, it also uses less water than conventional flushing. A method that isn't used very widely yet, but also conserves water, is called hydrojetting. It's most typically used to clean sewer lines and storm drains, but some utilities are using it for potable water applications. In hydrojetting, water is pumped at a high velocity, around 25 pounds per square inch, through a jetting nozzle head. The high pressure can be effective at removing buildup and uses about 75% less water than conventional flushing. This method is being used by utilities that still need to flush their lines during times of drought. Another methodology typically associated with flushing is continuous blow-off. For utilities that have numerous dead ends and severe water circulation problems, continuous blow-off or siphoning the system may be considered. Some utilities use an automated blow-off system with a timer. Because of low flow, blow-offs will not scour sedimentation, but it will help restore disinfectant residuals and reduce water age that can create consumer issues. Reducing pipe size in the affected area might be considered as a possible method of mitigating the problem. Some more general rules for flushing include: flushing velocities should be appropriate for the specific water quality objective. Lower velocities, 1 foot per second or less, might be used if the objective is to improve disinfectant residual or reduce water age. A higher velocity of 2.5 to 5 foot per second may be required to flush sediment or remove biofilm. Coordinate flushing crews so too many hydrants aren't open simultaneously. The resulting loss of system pressure could cause backflow and cross-connection problems. When flushing in a directional or isolated method, static gauges should be placed on the downstream hydrants for monitoring system pressure and residual. Doing so ensures adequate flow rates are being achieved. A pitot gauge should also be used when flushing multiple hydrants to calculate flow rates and to avoid backflow and cross-connection problems. Make sure crews open and close hydrants at a steady rate. Opening and closing the hydrants too quickly can cause a sudden change in water velocity called water hammer or hammering. Hammering can break pipes and valves and cause serious damage to the system. Hydrants used for flushing must be opened fully since the hydrant valve is not intended for throttling flow. A diffuser or some means of reducing the force of the water stream is preferred in certain locations, especially along unpaved areas. Based on requirements established by the U.S. EPA and administered by state agencies, all utilities are required to dechlorinate water released on the ground, which ultimately goes to the waters of the U.S. The only exception is when the water is pumped into the sanitary sewer system. Flushing hydrants should never be left unattended and should only be continued as long as necessary to ensure that the flushing is complete and the hydrant is operating properly. While many utilities flush during spring and summer daylight hours, night flushing offers certain advantages. Lower customer use at night means fewer customer complaints of service interruption. One disadvantage is that field workers must pay special attention to safety at night, since it is more difficult to see utility personnel. Flushing offers an opportunity for water quality monitoring and an opportunity to test for disinfectant residuals, turbidity, color, alkalinity or pH, coliform, iron and manganese, bacteria, disinfection byproducts, ammonia, nitrate, nitrite, and other tests of water quality. For older pipes or when flushing alone is not effective, more intensive cleaning may be required. Air purging, mechanical cleaning, or cleaning devices such as swabs and pigs may be used. Before cleaning, the system should be mapped, hydrants and valves should be tested, customers should be notified, and a list should be created detailing the order of work, the water sources, entry and exit points, and the disposal method of the flushed water. Installing bypass piping may also be something to consider to keep customers in service. The piping needs to be disinfected, flushed, and customers need to be converted to the bypass system prior to any cleaning effort. One method of cleaning is air purging. Compressed air is mixed with water and forced into the upstream end of the main after the blow-off valve is opened at the downstream end. Generally, small mains up to 4 inches or 100 millimeters are cleaned using this method, and the blasts of air remove all but the toughest scale. Swabs are another way to clean pipe. They are polyurethane foam plugs, slightly larger than the pipes they are placed into, then forced through with water pressure. Swabs can remove slime, soft scale, and loose sedimentation, but not hardened tuberculation. Unfortunately, swabs wear out quickly and must be frequently replaced. Swabbing procedures vary, but here are the basics. Notify the public and shut off the system. Install the equipment at entry and exit points to send and receive the swabs. Isolate the water main. Open the water valves upstream to send the swab and control speed. Using a pitot gauge, estimate the flow rate or meter on the inlet supply. Note the entry time, estimate the time of exit, and await the swab. If the swab becomes stuck, reverse the flow and time the return to determine the blockage location. Repeat swab runs until water becomes clear within 1 minute following the run. Always account for all of the swabs used. A typical cleaning operation will take from 10 to 20 swabs. Do a final flush to clear all swab particles. Pigs are stiff, bullet-shaped foam plugs that, like swabs, are forced through the main by water pressure. They differ from swabs, though, as they are denser and less flexible, but more durable. Pigs can remove more encrusted deposits, but their construction limits their ability to move through bends and fittings. There are 3 basic ways of inserting a cleaning pig into a main. One is to use a special pig launcher attached to a fire hydrant with the valve removed. For this method, an external water source is required. This can either be a fire hose connected to a hydrant that is not in the isolated section, or by a high-pressure pump connected to an independent water supply. Another method is to use an oversized spool inserted into the main line. Additionally, a Y section may be inserted into the line. After the pig has been forced into the main, it will be pushed along by water pressure from the distribution system. Pigging procedures will vary depending upon the condition of the pipeline, sections to be cleaned, and the type of pig used. The general procedure for pigging includes notify the public and shut off the system, install launching and retrieval equipment, isolate the water main to be cleaned and make sure all gate valves on the main to be cleaned are open, Make provisions to control surges. Open the water supply upstream to launch the pig. Time the pig and determine correct valve settings for desired speed. Control speed with downstream blow-off valve. Average speeds are 1 to 5 feet per second or 0.3 to 1.5 meters per second. Pigs traveling too fast will not clean as effectively and wear out quicker. Avoid sudden speed changes or stops. Always account for all used pigs. Run the final flush until the water runs clear. There are other types of cleaning that involve mechanical or power-driven systems or chlorine treatment. Metal scrapers are cleaning units pushed or pulled through mains that often contain spring-loaded steel blades of various shapes and sizes. Some are rigid, others freely rotate as they move through the main and dislodge tuberculation. The most effective way to incorporate scraping is to do it in conjunction with a lining process, cement mortar, or epoxy lining. It's been proven that with scraping alone, the biofilm has a tendency to build up sometimes at a faster rate than it accumulated before. In the cases of slime growth, chlorine may be used. The section affected is given a slug dose, usually 25 milligrams per liter, for 24 hours. The chlorine slug should be followed with thorough flushing to remove the chlorine and slime from the system. Customers must also be told to flush their service lines before using or consuming any water. Extensive flushing and cleaning programs can become expensive and time-consuming. However, the cost of emergency repairs or reactive flushing can also become costly. To cut down on cost and to save water, flushing programs should be coordinated with other distribution system preventive maintenance programs such as fire hydrant maintenance or valve exercising. Seasonal and responsive data can be logged for analysis along with water quality tests. Computer models help optimize a flushing program, but it is up to the distribution field operator to complete the work efficiently and effectively. No matter the methods chosen, a regularly scheduled flushing and cleaning program is an effective way to improve water quality while simultaneously maintaining the distribution system.